Welcome back. Section 3.4 Inverse of a matrix. Recall for a matrix n by n matrix Aij, its Ij minor of A is determinant of Mij, where Mij is a smaller matrix n minus 1 by n minus 1 submatrix of A obtained by removing the ith row and the jth column. Okay, so my Ij minor of A is determinant of that smaller submatrix, whereas the cofactor, ijth cofactor of A, you have to take in account the location, -1 to the power I plus j, determinant of Mij. Okay, that is the cofactor Aij. Further, determinant of A, you may expand along any row. For example, ith row, a1i multiplied by its cofactor plus a2i multiplied by its cofactor, so on. ai1 multiplied by its cofactor, ai2 multiplied by its cofactor, ain multiplied by its cofactor. Okay, choose any row and you can expand along it, or you can choose any column, that is fix the column j, a1j its cofactor, a2j its cofactor, all the way to anj its cofactor. What happens if we do not synchronize the cofactors with the column or row? That is, suppose I choose row 2 but use expansion cofactors along row 1. What happens if I don't synchronize accurately? Well, that brings us to a theorem. If Aij A is an n by n matrix, then expansion along row, you see, I'm using cofactor along row k, and I'm using entries along row I. So I have a different row entries chosen and different cofactors chosen. If I do that, I'll get 0 no matter what. Okay. Likewise, if I use a column j for my little elements aij, but cofactor along column k, then also I'll get 0. Okay. Fix row I and row k. Okay, so I'm trying to prove the first statement. Fix row I and row k. Consider matrix which is considered from matrix A, where row I of A is replaced by row k of A. So I have replaced an entire row by another row. Then the matrix B is singular because 2 of its rows are identical. 2 of its rows are identical. Now that's dangerous. It means, you see, if you try row echelon form, you can immediately subtract and you get a row of zeros. If you have a row of zeros, then determinant is 0. Now, kth row of B is ai1, ai2, ain. Why did I use I? Because remember, I replaced the kth row by the ith row. So ai through ain, whereas the cofactors are ak 1 to akn, which means, you see, my determinant B, where I have 2 rows identical, I'm using kth row and its k factors, so that is determinant. Determinant is 0. That means I have this expression which is exactly what we wanted. Okay. The statement for expansion along column holds because determinant of a matrix A or matrix M is same as determinant of its transpose. So whatever you discuss for column, for row can be discussed for column using this theory. Here is example. How do you let's look at a concrete example. Let A be this matrix 3 by 3. Okay. Let's expand along row 2. So I'm using row 2 elements -1, 2, -5. But I'm using cofactors along row 1. That is, I drop first row, first column, find its matrix, drop first row, second column, drop first row, third column. So I'm using cofactors along row 1. Let's look at A11. Drop first column, first row. That's my submatrix. You're going to find its determinant and multiply by -1 to the power 1 plus 1. Okay. Likewise, A12. Drop row 1 and column 2. Whatever is left is my matrix, submatrix. Find its determinant, multiply by -1 to the power 1 plus 2. That's the cofactor. Then A13, drop first row, third column. Whatever is left, write it down, find its determinant, multiply by -1 to the power 1 plus 3. Okay, so remember, I'm using second row entries and first row cofactors. Calculate, assume my calculations are correct, check for yourself. 10 minus of -20, so that's positive 30 with a positive 1. -5 minus 0, -5 times -1, that's a positive 5. -4, 0, -4 times positive 1 is -4. So substitute these values here. What do you get? -30 plus 10 plus 20. Okay, so it's a 0. So we used expansion along row 2, but cofactors along row 1. So if you do not synchronize, you will always get 0. So that's not good. So let's try with columns. Suppose I'm expanding along column 2. So I'm using 3, 2, 4, but cofactors along column 1. Okay, so this A11 cofactor, this is A21 cofactor, this is A31 cofactor. Similar calculation, A11 cofactor, drop its column and row, whatever is left behind, keep track of the sign using -1 to the 1 plus 1. What about A21? Drop column 1, row 2, 3, 4, 4, 5 is remaining. Keep track of its sign. Then A31, drop its row and column, 3, 4 to -5, and keep track of its sign to find the cofactor. Calculations, 10 minus -20, so that's a 30 with a positive. 15 minus 16, that's a -1 with a negative, positive 1. -15 minus 8, -23 with a positive, -23. So these are the numbers here. You're going to multiply. Well, you get 0 expectedly. All right, here is a definition. So, okay, before I move on, so this is an important result, guys. What this says, you have to synchronize. If I'm using a certain row expansion, then you make sure your cofactors is along that same row. If you're using a column expansion, make sure your cofactors are along the same column. So it's very important. If you do not synchronize, then you will get 0 always. Okay. Okay, inverse of a matrix. Let Aij be an n by n matrix. The n by n matrix ADJA. That stands for adjoint of A. So start with a matrix. You're going to build another n by n matrix called adjoint of A, whose ijth entry is the cofactor. Notice the change in index AJI. So ijth entry will be AJI cofactor of matrix A. Okay. So you see, notice this is A21, this is A31, right? So it's like a transpose or something, but that's called adjoint matrix. So find the cofactors for each ij and replace it as a transpose, right? A1, instead of writing A21 here, you have A12 here. Instead of having AN1 here, you have A1N. Okay? So this is called the adjoint matrix. Recall what is the cofactor Aij? Negative 1 to the power I plus j, determinant of a submatrix. Remove the ith row and the jth column. That matrix, its determinant, that's called minor. Minor times an appropriate sign is your cofactor. Let's look at this example. Whoa. So that's a construction of adjoint matrix. Okay. So what did we do? There are 9 entries. For each entry, find its cofactor. So that is A11. Drop this, 2, negative 5, 4, 5. For A11, 2, negative 5, 4, 5. For A11, 2, negative 5, 4, 5 with the sign that is A11 cofactor. I have calculated, that's 30. That entry, that is 1, 2, first row, second column. So drop row 1, drop column 2, negative 1, negative 5, 0, 5. Negative 1, negative 5, 0, 5. That was 1, 2 location. So that's the sign. Assuming my calculations are correct, that's A12. Likewise, here, that's 1, 3. Drop row 1, drop column 3. Negative 1, 2, 0, 4. Negative 1, 2, 0, 4. That was 1, 3. Don't forget the sign part of it. Assuming my calculations are correct, this is my answer. Okay. Here, now this location, row 2, column 1. So drop row 2, drop column 1, 3, 4, 4, 5. 3, 4, 4, 5. You have dropped row 2, column 1, 2, 1. Okay, so that's the appropriate sign. Assuming my calculations are correct, that's that. Okay, so I have done it for every single location. You will have to check for yourself, make sure you do. You get these entries. Okay, all these cofactors for every entry. Okay, there are 9 such. Now arrange them. A11 here. Instead of A21 there, you have A12 there. So A12 is here. Okay, let me move my cursor away so you can see. That's the adjoint matrix of A. Okay, check for yourself. That's my matrix A. That was the adjoint matrix. When you multiply, you get diagonal matrix 59s. You'll have to check for yourself. Okay. Further check. You see the original matrix determinant A. I'm expanding it along row 1. 2 times submatrix, 3 times submatrix. Notice cofactor gets you the sign. And you get that to be 59. So that's the magic we are looking for. Okay. Let's continue in the next video.